Welcome to the deep dive. Today, we are taking on a figure so foundational to modern thought, it's easy to feel like we already know him. I'm talking about Sir Isaac Newton.
Right.
But the simplified image we hold, the genius who merely happened to be sitting under an apple tree, it hides a truth that is far stranger, more contradictory, and ultimately far more compelling.
That's exactly where the sources become so essential. Because when you actually analyze the entire historical record, you see a figure of just unparalleled intellectual rigor, the public scientist who defined math and physics for centuries.
The man we all learn about in school.
Precisely. But he's existing simultaneously with this deeply secretive private man. I mean, this was someone obsessed with pursuits his contemporaries might have labeled heresy or, even black magic.
What are we talking about here?
We're talking about complex, unorthodox theology and an extensive, decades-long devotion to alchemy.
Okay, so let's unpack this monumental life. Our mission for you, the intellectually curious learner, is to move far beyond the famous Principia and the laws of motion. We are plunging into his golden years of secretive discovery.
Yes.
His controversial spiritual beliefs that he had to hide from the Anglican Church, his highly effective real-world role reforming the nation's coinage, and, why historians like the physicist James Jeans were compelled to call him perhaps the greatest intellect the human race has seen.
We're examining a polymath in the truest sense of the word. You have Newton, the mathematician, the physicist, the astronomer, the theologian, the alchemist, and crucially, the master of the royal mint.
It's an incredible list.
It is. And his collected work is rightly considered the most influential in bringing forth modern science and, really igniting the Enlightenment. Yet his personal reality was this intense, often volatile blend of rigorous rationality and profound occult interest.
So let's start at the beginning, because to understand the towering figure of the adult Newton, I think we have to look at the unstable foundation he was built on.
Precisely. His was a difficult and unstable start. He was born prematurely on Christmas Day, that's December 25th, 1642, under the Old-Style calendar, which translates to January 4th, 1643, in the New Style at Woolsthorpe Manor in Lincolnshire.
And his father died before he was even born.
That's right. Before he ever knew him, his father, who was also named Isaac Newton, died 3 months before his birth.
So he was born into loss, and then a few years later he experienced what seems like a profound abandonment. His mother, Hannah Ayscough, remarried.
She did. She married the wealthy Reverend Barnabas Smith when Newton was only 3, and she moved away to live with her new husband, leaving young Isaac to be raised by his maternal grandmother.
That's a massive psychological shock for a small child. You can't overstate that.
It was, and the intensity of his resulting resentment is, it's shockingly documented in his own hand. We have a surviving list of sins he wrote down that he had committed up to the age of 19.
A list of his own sins.
Yes, and among those entries, you find this revealing and, frankly, pretty alarming insight. He wrote, threatening my father and Mother Smith to burn them and the house over them.
Wow.
This is the psychological foundation of the man who would later define the universe with cold, elegant laws. He was intensely driven, often ruthlessly competitive, and you have to think those traits may well stem from this early instability and this need for control.
So after an initial period of schooling at the King's School in Grantham, his mother, who was widowed again, tried to make him a farmer.
Right.
An utterly miserable detour for someone whose mind was clearly already operating at a different frequency.
Oh, it was a very brief but miserable period for him. He absolutely hated the idea of farming. But his time at King's School, from age 12 to 17, was essential because he had already gained a significant foundation in mathematics and geometry there.
He was already standing out.
He was. He distinguished himself by building these complex physical objects like sundials and remarkably intricate working models of windmills. He only got to return to school after persistent persuasion from his former master Henry Stokes and his uncle, Reverend William Ayscough. They saw his potential.
And that's what cleared his path to Trinity College, Cambridge in 1661. But he didn't start privileged. We often forget that part of the story.
He definitely had the hustle. Yeah. He was admitted as a subsizar, which meant he had to perform menial valet duties for wealthier students just to put his way. It wasn't until 1664 that he secured a scholarship. And that provided the financial stability he needed to complete his BA in August 1665. And it's during these university years that he moved from reading the classical curriculum of Aristotle to absorbing the work of modern thinkers like Descartes and Galileo.
And that leads us to the great turning point. Just as he finished his degree, fate, you could say, intervened, shutting down the entire academic world.
The famous closure of the university due to the Great Plague. Newton returned to the quiet of his childhood home in Woolsthorpe for nearly 2 years. And this period, 1665 to 1667, is arguably the single most productive individual period in the entire history of science.
It's the origin story of modern science itself, really.
I mean, Louis Trenchard Moore, one of his biographers, described it as the richest and most productive ever experienced by a scientist. He even suggested there are no other examples of achievement in the history of science to compare with that of Newton during those 2 golden years.
It was just an explosion of solitary genius.
Totally. Powered by his own furious drive and a massive intellectual appetite.
And during those 2 years, he laid the groundwork for the trio of discoveries that would change the world. You have the initial development of his theories on infinitesimal calculus, which he called fluxions, the fundamental principles of optics, particularly his theory of color, and of course the formulation of the law of universal gravitation, all conceived and developed in complete intellectual isolation.
And we also get glimpses into the mechanics of his organized mind during this period. The sources describe him as exceptionally organized when it came to his note-taking.
What does that mean exactly? What was he doing?
Well, he would dog-ear important pages, and his indexes, which were alphabetical, by topic, look remarkably like the indexes we use today for quick reference. And this organization was absolutely critical because the sources identify him as a Genusian thinker, named after the two-faced Roman god Janus.
A Genusian thinker. What does that mean in an academic context?
It means he had this rare ability to look simultaneously in 2 disparate directions. He could mix and combine seemingly unrelated fields like, say, geometry and heat transfer, or astronomy and theology, to get these creative breakthroughs.
That makes so much sense.
This ability to synthesize across intellectual boundaries, it definitely explains his later forays into alchemy and theology alongside his rigorous physics. His mind was structured, but it wasn't limited.
So, in 1667, the plague subsides, and he returns to Cambridge. He's elected as a Fellow of Trinity in October. But stability brought its own crisis, the requirement that all fellows take holy orders as Anglican priests.
And this was a ticking time bomb, because Newton had privately and fundamentally rejected the central doctrine of the Anglican Church.
At the Trinity.
He wasn't just ambivalent, he actively rejected it.
He did. He was, in secret, an unorthodox Christian, possibly a Socinian sympathizer or an Arian. The idea that Jesus Christ was co-equal with God the Father was, in his eyes, a later corruption of Scripture, and so for him, worshiping Christ as God was idolatry.
That is a life-altering, potentially career-ending, or even fatal heresy in 17th century England. How on earth did he navigate that risk?
He was incredibly cautious and, frankly, politically astute. He succeeded his mentor, Isaac Barrow, as the Lucasian professor of mathematics in 1669 at only 26 years old.
An amazing achievement at that age. It was. And he successfully argued that this prestigious position should exempt him from the ordination requirement, emphasizing the time needed for his profound scientific studies. This request was actually accepted by King Charles II, which averted a major public conflict with Anglican orthodoxy that could have completely ruined him.
It's fascinating, then, that the same position that saved his career was the one he seemed to care least about in terms of its contractual duties.
That's the great irony. Despite being the Lucasian professor, he was notoriously terrible at the actual teaching part.
Really?
Oh, yeah. Biographical accounts suggest his classes were almost always empty. His assistant noted that Newton would arrive on time, and if no one showed up, he would just cut the lecture time from 30 minutes to 15, talk to the walls for a bit, and then retreat to his experiments or his private studies.
So he was just checking a box.
Exactly. He fulfilled his contractual obligation to lecture, but he enjoyed neither teaching nor students. It paints this picture of a man who valued intense personal study and discovery, far, far above public engagement.
So having established the psychological engine and that initial burst of solitary genius, let's focus on the staggering output that followed. The sources claim that Newton's work managed to distinctly advance every branch of mathematics then studied. And he was almost entirely self-taught in the subject.
Yeah, the historian Richard S. Westphal confirmed this. He wrote that, by every indication we have, Newton carried out his education in mathematics and his program of research entirely on his own. He started developing calculus, or fluxions, as he called it, as early as 1664.
Wow.
And by May of 1665, he was already at the point where he could compute tangents and curvature of continuous curves, and he was recording these definitive tractates in his private waste book.
This brings us directly to, I think, the most famous intellectual feud of the time.
Yeah.
The calculus priority dispute with Gottfried Wilhelm Leibniz.
Yes. The controversy was bitter, it was fueled by nationalistic pride, and it seriously marred the later lives of both men. And while both of them independently invented the principles of calculus, the evidence is pretty overwhelming that Newton formulated the core ideas years earlier than Leibniz.
He was way ahead.
He started his work almost a decade before the German polymath published his findings.
But the irony remains that the elegant, highly functional notation we use universally today, the Dichtstätte, is Leibniz's invention, not Newton's.
Exactly.
Right.
Leibniz's notation was adopted across continental Europe for its convenience in representing integrals and derivatives. Newton's notation, which used dots over variables to represent fluxions, is still widely used in physics for things like time derivatives. But yeah, Leibniz's approach ultimately won the day for general mathematical use.
But there's a twist there, right, about how modern mathematicians view Newton's original work.
There is, and it's truly fascinating. Roger Penrose noted that Newton's original geometrical methods were often more concise and elegant than the formal calculus that replaced it, and Vladimir Arnold went even further.
What did he say?
He stated that comparing Newton's original texts with later commentators reveals how Newton's presentation is often more modern, more understandable, and richer in ideas. See, Newton was obsessed with limits and ratios, what he called the method of first and last ratios, which allowed him to avoid the philosophical quagmires of infinitesimal quantities that really plagued his contemporaries.
So the very tool we use to understand his work might actually be hiding the elegance and depth of his original geometric thinking? That's a profound shift in perspective.
It really is. And beyond calculus, the sheer scale of his mathematical achievements is just breathtaking. His first major breakthrough was the generalized binomial theorem, which he discovered around 1664-65.
Why was that theorem so powerful and significant? What did it unlock?
Well, before Newton, the binomial theorem, which tells you how to expand expressions like a plus b to a power, it only worked if the exponent was a positive integer.
Okay, pretty limited.
Right. Newton generalized this theorem, so it could be applied to fractional or negative exponents. And this discovery provided a powerful new tool for handling complex algebraic expressions, and crucially, it allowed him to easily approximate the area under curves. It was essentially a massive shortcut for integration.
A foundational tool.
It was instantly hailed as one.
And he didn't stop there. We see his name attached to methods that are still central to computation today.
Absolutely. He developed Newton's method for approximating roots of a function, which is fundamental to numerical analysis. He also created the Newton polygon and originated the Newton-Cotes formulas for numerical integration. And even more surprisingly, he pioneered the modern application of Gaussian elimination in Europe.
Gaussian elimination is something taught in basic linear algebra today.
Yeah.
What was his contribution to that?
So in 1669-70, Newton noted that the existing algebra books just lacked a clear, systematic lesson for solving simultaneous equations. So he supplied that method, basically the organized process of substitution and row reduction we know today, and established the key terminology of extermination, which we now call elimination.
So he wrote the textbook, essentially.
He provided the first practical, systematic guide for efficiently solving systems of equations, which was critical for things like astronomical calculation.
And he initiated an entire new branch of applied math, the calculus of variations.
He did. This is the field that deals with finding the functions that minimize or maximize a certain quantity. He kicked it off by formulating and solving Newton's minimal resistance problem in 1685.
Which was?
Finding the optimal shape of a body to experience minimum drag. Then in 1697, he famously solved Johann Bernoulli's really challenging Brastochrone curve problem. That's the curve down which a bead falls in the shortest time. And he did it in a single intense night of work.
One night.
One night. And that resistance problem is still regarded as one of the most difficult tackled by variational methods prior to the 20th century. He also pioneered vector analysis, introducing the notion of the vector in Principia, treating physical quantities like velocity, acceleration, and force as directed quantities, which is, central to all modern physics.
Let's shift gears from pure mathematics to optics, another field he fundamentally reformed during those golden years. And it all begins with a pretty simple experiment using a prism.
It was revolutionary in its simplicity. Around 1666, Newton passed sunlight through a single prism, and he observed that the resulting spectrum, when he projected it, was oblong, not circular, even though the source light was circular.
And from that simple observation,
From that, he came to the radical conclusion. Color is not generated by the prism. It is intrinsic to light itself. The prism simply separates the existing colors because it refracts different colors by different angles.
This laid the bedrock for all color science.
Crucially, yes. He proved that colored light does not change properties upon reflection or scattering. So color is the result of objects interacting with already colored light, not the object generating the color itself. And this immediately revealed a major problem with the technology of the day.
The telescopes.
Exactly. He concluded that refracting telescopes, which use lenses, would always suffer from chromatic aberration, that blurring of colors caused by the lens refracting different wavelengths unevenly.
And being Newton, he didn't just diagnose the problem, he invented the solution, the Newtonian telescope.
Yes, as a practical demonstration, a proof of concept, he built the first known functional reflecting telescope, which used mirror instead of lenses, to eliminate that chromatic aberration.
Which must have been a huge engineering challenge.
Tremendous. He had to invent the technique for grinding his own highly reflective speculum metal mirrors, and he even used the phenomenon of Newton's rings, these interference patterns he observed, to judge the quality of the precise shape of his optics.
His methodology was also decades ahead of its time, wasn't it? Particularly in dealing with imperfect data.
His approach to measurement was incredibly sophisticated. In his studies of Newton's rings, he introduced what he called an error-slaying method, systematically averaging differences and reducing noise in his measurements in a way that was just unprecedented in the 17th century.
And he applied this elsewhere.
He did. He applied this rigor later to astronomical studies, and historians now credit him with inventing a technique we know today as linear regression analysis by averaging data sets and summing the residuals to zero. He basically treated measurement error like a separate problem to be solved mathematically.
And finally, his views on light itself hold a surprising modern twist. For a classical physicist, he was remarkably close to anticipating quantum mechanics.
It's true. Although the classical view holds him up as the champion of the corpuscular or particle theory of light, Newton was never fully satisfied with it. He noted in his seminal work Optics that light had both particle-like and wave-like properties.
Wave-particle duality.
He was trying to reconcile these two aspects, really anticipating the concept of wave-particle duality. The physicist David Finkelstein actually called him the first quantum physicist for this attempt to bridge the two descriptions.
And if we want a dramatic illustration of his power as an experimentalist, we need to talk about the sheer intensity of his burning mirror.
Right. So in 1704, he presented a burning mirror made of 7 concave glass mirrors. The estimated radiant energy it achieved was a staggering 460 watts per square centimeter.
I can't even picture what that means.
Well, the intensity was so extreme. It was described in one account as being certainly brighter thermally than 1,000 suns, that historians suggest it may have produced the greatest intensity of radiation brought about by human agency before the arrival of nuclear weapons in 1945.
That is incredible.
Reports noted that it could make metals smoke and even boil gold. It wasn't just theoretical. His practical skill could harness immense physical power.
All of this mathematical and optical work, it feels like it served as preparation for the single masterpiece that anchored his fame, the Philosophiæ Naturalis Principia Mathematica. But the impetus for returning to celestial mechanics actually came from a renewed correspondence with a rival.
That rival was Robert Hooke, the Secretary of the Royal Society in 1679. And it was Hooke who spurred Newton to work out the critical proof, demonstrating mathematically that elliptical planetary orbits must result from a centripetal force inversely proportional to the square of the radius vector.
And this leads to the monumental publication in 1687, and we really owe a debt of gratitude to Edmund Halley for encouraging and financially supporting its printing.
Halley's role was absolutely crucial. The Principia might have just remained a set of notes otherwise. The core achievement was, it was the first great unification in physics. It established classical mechanics and formulated the 3 universal laws of motion and the law of universal gravitation, defining a single set of rules for the entire cosmos.
The scope of what these laws explain must have felt like, uncovering the mind of God to his contemporaries.
It was completely transformative. The implications were truly universal. These laws explained everything from an apple falling on Earth to the precise motion of celestial bodies. Using gravity, Newton was able to derive Kepler's laws of planetary motion.
Account for the tides.
Yes, account for the regular behavior of ocean tides, explain the trajectories of comets, and even detail the slow wobble of Earth's axis, the precession of the equinoxes. This body of evidence just effectively eradicated all remaining scientific doubt about heliocentricity.
He also gave us the first quantitative metrics for the solar system, right?
That was vital for establishing a universal scale. Newton provided the first quantitative estimate of the solar mass and determined the masses and densities of Jupiter and Saturn. This application of a universal law to specific measurable bodies was hailed as the supreme expression of the doctrine that one single set of physical concepts applies to all matter everywhere in the universe.
But the work on gravity came at a serious human cost. There's a deeply revealing anecdote about the intellectual difficulty he faced when applying his theory to the motion of the moon.
The complexity of applying the three-body problem, the gravitational interactions between the Earth, the Sun, and the Moon, was just mathematically profound.
Right.
And Newton's biographer reported that working on this specific problem in the early 1690s caused him a severe loss of appetite, acute sleep deprivation, and intense headaches. He even confessed to an astronomer that his head never ached but when he was studying the subject, and he resolved that he would eventually think of it no more.
It was literally hurting him to think about it.
It was intellectually debilitating. It shows the immense mental toll of his greatest work.
We tend to focus only on the laws of motion and gravity, but Book 2 of the Principia is a foundational text for an entirely different field, fluid mechanics.
It really is. Book 2 was a critical pioneer. It provided the first comprehensive quantitative treatment of motion under resistance. So, how objects move in the real world through air or water. He formulated the linear relationship between shear stress and strain rate that defines a Newtonian fluid.
Things we still use today.
Every day. He analyzed Couette flow and studied the resistance of axisymmetric bodies. He was solving problems that wouldn't really be tackled again until the 20th century.
And his scope extended beyond mechanics and fluids.
Oh, yes. In the Principia, he inferred the oblateness of Earth's spheroidal figure, the fact that it bulges slightly at the equator, a prediction later confirmed by geodetic measurements. He also performed experiments to calculate the age of the Earth and described a precursor to the modern wind tunnel.
It just keeps going.
It does. Separately, in 1701, he formulated the empirical law of cooling, which was the first heat transfer formulation and the formal basis of convective heat transfer. Even in sports physics, he was the first to explain the Magnus effect, how spinning objects curve in flight, based on observing tennis players at Cambridge in 1672. The sheer breadth is just astounding.
And all of this incredible output rests on a fundamental philosophical declaration that became the motto for the scientific revolution. Hypotheses non fingo. I frame no hypotheses.
This assertion, which he famously placed in the concluding general scholium of the Principia, was a strategic declaration of his method, but it was also a direct shot at his critics, particularly the Cartesians.
Who were complaining about what, exactly?
They accused him of introducing an occult agency by postulating an invisible force gravity acting over vast empty distances without explaining how it worked.
So his response wasn't, this is how gravity works, but I don't need to hypothesize on how it works, only that it works.
Exactly. He insisted that whatever is not deduced directly from phenomena is merely a hypothesis. And hypotheses, whether metaphysical, physical, of occult qualities, or mechanical, have no place in experimental philosophy.
So his rules became the bedrock of modern science.
They did. Admit only sufficient and true causes, assign the same causes to the same effects, generalize qualities of bodies found universally, and treat observation-derived propositions as accurate until contradicted by other observations.
This established a new, highly rigorous scientific method. It wasn't enough to just predict the movement of the planets. The phenomena had to accurately measure the theoretical parameters, forcing scientists to use provisional propositions to guide successive approximations toward the truth.
It was a philosophical statement demanding empirical grounding. He said, it is enough that gravity really does exist and acts according to the laws we have set forth, and is sufficient to explain all the motions of the heavens and the sea. It was a firm line drawn between mathematical description and metaphysical speculation.
Now we enter the shadows, the side of Newton that was hidden for centuries. We've described the hyper-rationalist of the Principia, but that man was spending most of his time elsewhere.
That's the great paradox. And we know that over half of everything Isaac Newton wrote concerned theology and alchemy. Of his estimated 10 million words of writing, approximately 1 million deal with alchemy alone.
1 million words.
It was an enormous, decades-long, secretive commitment.
And we can verify his true range of interests by looking at his library, which truly changes the perception of his priorities.
It absolutely does. His personal library contained 1,752 books. When you categorize them, Works on theology represented the largest section 477 books, about 27.2%, and alchemy made up a substantial portion, 169 books or 9.6%.
And how does that compare to his main fields?
Well, these two categories vastly outnumbered his core scientific texts. Mathematics accounted for only 7.2%, and physics for just 3.0%. He was arguably more devoted to finding the true chronology of the Bible and the Philosopher's Stone than he was to publishing advanced mathematics.
Let's start with his controversial religious beliefs. He was devout, but his views would have been considered extremely dangerous heresy.
He was a private heretic. He rejected the doctrine of the Trinity, siding with Arius, who held that Christ was a divine mediator, but ultimately a creation of and subordinate to God the Father. Newton profoundly believed that worshiping Jesus Christ as God was idolatry, the grievous sin, a belief he had to hide meticulously because it was punishable by law.
It's amazing he kept this secret while maintaining such a high profile at an Anglican university.
He was a master of self-concealment. He went to great lengths, engaging in extensive biblical scholarship, including detailed textual criticism, to prove that the standard texts had been corrupted. His work included an historical account of two notable corruptions of Scripture.
He's applying the same rigor to ancient texts as he was to planetary orbits?
Precisely. He also applied his computational rigor to theology, producing complex biblical chronology where he calculated the precise date of the crucifixion to be 3 April AD 33.
And his contemporaries had no idea.
Well, despite his private heresy, he was respected as a theologian by them. The Archbishop of Canterbury, Thomas Tennyson, once told him, "You know more divinity than all of us put together." But that admiration was based on a false premise. They never knew the full extent of his Unitarian beliefs.
Now for the alchemy. It wasn't a casual hobby. It was a decades-long, intensive pursuit that may have physically damaged him.
Right. Alchemical texts were always coded with allegory to protect craft secrets, which made them perfectly suited to Newton's intensely private, complex mind. But this pursuit had a very dark side.
The mercury.
Yes. When his death mask was examined posthumously, his hair was found to contain high levels of mercury. This was almost certainly the result of his alchemical experiments, which often involved heating and handling mercury and other toxic metals.
And mercury poisoning is the leading theory to explain his eccentricity and the nervous breakdown we mentioned earlier.
That's the consensus among scholars. Mercury exposure, especially chronic low-level exposure, is known to cause paranoia, emotional instability, and wild swings in temperament. This fits perfectly with the breakdown that occurred around 1693.
Which coincided with what?
With the abrupt end of his close friendship with the Swiss mathematician Nicolas Fatio de Deulier.
Tell us about that breakdown. What did it look like?
It was severe. During this period of paranoia and emotional instability, Newton sent these wildly accusatory letters to close friends, including the philosopher John Locke. He charged Locke with trying to embroil Newton with women and by other means.
Which was completely unfounded.
Completely unfounded and irrational. And Newton later apologized, blaming lack of sleep. But it was a clear, documented moment where the intense pressure and likely the mercury poisoning overwhelmed his otherwise rigorous mind.
And speaking of bizarre notes, his alchemical notes also revealed what he thought was the best cure for the plague.
This is a stark reminder that even the greatest scientific mind existed during an era when science and superstition were still deeply intertwined. Analyzing his notes from the 1660s plague years, Newton suggested a therapy based on the work of Jan Baptist van Helmont.
And what did it involve?
The cure involved suspending a toad by its legs in a chimney for 3 days until it vomited up earth and insects onto a dish of yellow wax and then died. The powdered toad, combined with its secretions, would be made into lozenges and worn about the affected area to drive away the contagion.
A mixture of empirical observation and pure occult practice.
Exactly.
Let's turn to his intense personality. We know he was incredibly driven, prioritizing work over health and controlling his physical appetites, even becoming vegetarian later in life. But he was complex, neurotic, and fiercely competitive.
He definitely presented two faces. On one hand, he expressed this profound humility, writing, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, whilst the great ocean of truth lay all undiscovered before me."
A beautiful quote. Yet, we know he was intensely sensitive to criticism and held massive grudges against intellectual rivals, most famously Robert Hooke, which brings us to perhaps the most misunderstood quote in science history. "The shoulders of giants."
Ah, yes. The full quote is, "If I have seen further, it is by standing on the shoulders of giants." While it's typically celebrated as a statement of modesty, many historians believe that in the context of his vicious, ongoing dispute with Hooke in 1675, it was intended as a cruel personal attack.
Oh, so.
Hooke was noted for being physically short and hunchbacked. So even though the underlying proverb suggests the speaker is the dwarf who sees farther, using that specific language in a letter to his rival is highly suspicious. It suggests a streak of profound intellectual malice.
Around the age of 53, Newton made this dramatic career pivot, leaving the empty lecture halls of Cambridge for the high-stakes world of London government. This is where the hyper-theoretician becomes the hands-on executive.
He became the Warden of the Royal Mint in 1696, a position he got through the patronage of his friend Charles Montague. He was later promoted to Master of the Mint in 1699, which was a highly lucrative position he held for the last 30 years of his life.
And these were usually do-nothing jobs, right?
They were typically sinecures, jobs that paid well for very little work, but Newton treated them as vital duties. He retired from Cambridge entirely in 1701 to focus on it.
The Mint appointment put him in charge of managing a massive national crisis, the Great Recoinage of 1696. What was the central problem facing the country?
The currency was collapsing. It was due to widespread counterfeiting and specifically clipping. People would shave small amounts of silver off the edge of hammered coins and then hoard the silver scraps.
So the coins in circulation were worth less than their face value.
Much less.
Yeah.
Since coins were valued by weight, not just denomination, the silver content of the currency had plummeted. Newton estimated a staggering 20% of the coins taken in during the recoinage were counterfeit or clipped. The national economy was at serious risk.
And this is where the genius theoretician becomes an incredibly effective, bureaucratic, and often ruthless crime fighter.
It's one of the most surprising twists of his life. Counterfeiting was considered high treason, punishable by hanging, drawing, and quartering. Newton personally took charge of the enforcement. He knew he couldn't rely on the existing, often corrupt, constables.
What did he do?
He developed an intelligence network. He personally investigated cases, often disguising himself as a patron of bars, taverns, and criminal haunts, just to gather evidence.
He was a master physicist turned master detective.
He was meticulous. Between 1698 and 1699, he conducted over 100 personal cross-examinations of witnesses, informers, and suspects. He used the same relentless, systematic interrogation style he used on abstract problems, exploiting the weaknesses in their testimonies until the truth was revealed.
And he got results.
He successfully prosecuted 28 coiners, ensuring they faced the full penalty of the law. This included the infamous serial counterfeiter, William Challoner.
Challoner was a formidable opponent, wasn't he?
He was. Challoner was a master confidence man and counterfeiter who had nearly outmaneuvered the law. He had previously used bribery and perjured testimony to escape prosecution.
But Newton was different.
Newton, seeing Challoner as a genuine threat to the stability of the entire economy, personally gathered the damning evidence. Challoner tried everything, appealing to Newton's vanity, claiming innocence, sending desperate letters. But Newton was unyielding. He treated Challoner's downfall with the same intellectual rigor as he treated a physics proof. Challoner was found guilty and hanged at Tyburn in 1699.
Did he apply his scientific mind to the actual industrial process of minting?
Absolutely. He used his unique combination of organizational skill and engineering genius to streamline the mint's operations. He dramatically improved minting technology, raising the weekly coin output from 15,000 pounds to an impressive 100,000 pounds.
And the quality.
More importantly, he introduced unprecedented quality control. He reduced the standard deviation of guinea weights from 1.3 grams to just 0.75 grams, increasing the accuracy and uniformity of British coinage. These improvements lasted until the 1770s and saved the Treasury massive sums.
Beyond production, he was also influencing national economic policy with surprisingly modern views.
He was way ahead of his time. He believed that paper credit, such as government debt, was a practical and wise solution to lower interest rates, which would in turn stimulate trade and growth, a view often debated at the time.
And he had a radical view on what gave currency its value.
He did. He held the radical minority opinion that the value of both metal and paper currency was fundamentally set by public opinion and trust, a social concept, rather than simply the intrinsic material value.
And his most definitive economic action inadvertently shifted the basis of the national currency.
That's right. His extensive report in 1717 led to a royal proclamation that definitively changed the bimetallic ratio between gold guineas and silver shillings. The new ratio favored gold, and the long-term effect of his adjustment was to inadvertently move Britain from the silver standard to its first operational gold standard.
Despite his profound success at the Mint, his brief foray into parliamentary politics was far less illustrious.
Yeah, he served 2 short, largely unremarkable terms as a member of parliament for the University of Cambridge. There's a famous anecdote suggesting his only recorded comments during one term were to complain about a cold draft in the chamber and politely request that the window be closed.
He clearly preferred the systematic precision of the Mint to the messy chaos of politics.
No question.
And even the greatest minds are not immune to financial speculation, particularly during the heady days of the South Sea bubble.
No, even the supreme rationalist fell victim to the hysteria.
Yeah.
He lost a staggering amount, at least £10,000 and plausibly over £20,000 in the collapse of the South Sea Company around 1720.
And he had a famous quote about that, didn't he?
He supposedly remarked afterward that he could calculate the motions of the heavenly bodies, but not the madness of the people. Fortunately, he was already rich before the bubble, so he still died a very wealthy man.
He received his knighthood later in life, an honor that recognized his status.
He was knighted by Queen Anne in 1705, making him only the second scientist to receive the honor after Francis Bacon. Historians suggest this knighthood was likely motivated by political considerations connected with the parliamentary election that year, rather than solely recognizing his scientific work or his service at the Mint.
Those certainly provided the pretext.
Of course.
Newton died in his sleep in London on March 31st, 1727, New Style. What kind of farewell did the world give the man who had defined it?
It was a monumental event. Given his revolutionary status, he was given a highly ceremonial funeral attended by nobles, scientists, and philosophers. And he was buried in Westminster Abbey among kings and queens, a testament to his status. He was the first scientist ever granted burial there.
We must definitively address the persistent, charming myth surrounding his greatest discovery, the Apple story. We all know the popular version, but what did the sources actually record about the event?
Well, the story is a wonderful piece of scientific folklore, passed into popular knowledge largely by Voltaire, who heard it directly from Newton's niece, Catherine Barton.
So it comes from the family, in a way. But what's the reality, according to his contemporaries who recorded the event?
Acquaintances confirm Newton did tell the story, but the apocryphal detail of him being struck on the head is definitely false. William Stukeley's account, recorded in 1726, quotes, Newton recalling the event, contemplating why the apple always descends perpendicularly, always toward the Earth's center.
Okay.
This led him to hypothesize a drawing power in matter that extends not just to the surface, but all the way to the Earth's core.
So the apple provided the moment of introspection, the critical question, not the immediate mathematical answer.
Exactly. It prompted him to grapple with the idea that terrestrial gravity extends to the moon in an inverse square proportion, which he was working on as early as the late 1660s. The crucial missing piece, the scientific gap that took him 2 decades of intense mathematical struggle, was proving that the Earth's gravity acts as if all its mass were concentrated at its center point.
That was a real work.
That highly complex proof was the 20-year battle, not the simple fall of the apple.
The acclaim he achieved, both in his time and posthumously, places him in a class by himself. You simply can't overstate the impact of his life's work.
No, you can't. The sources are full of hyperbolic yet genuinely earned praise. Joseph Louis Lagrange called Newton the greatest genius who ever lived, and he added, the most fortunate, for we cannot find more than once a system of the world to establish.
Even Einstein.
Albert Einstein himself, someone who later superseded aspects of Newton's work, stated that Newton's creation of calculus in relation to his laws of motion was perhaps the greatest advance in thought that a single individual was ever privileged to make.
James Gleick's assessment cuts right to the core of his achievement.
Gleick wrote that Newton discovered more of the essential core of human knowledge than anyone before or after. And Ludwig Boltzmann simply called Principia the first and greatest work ever written about theoretical physics.
So where do historians rank him?
This immense respect places him generally alongside Carl F. Gauss and Archimedes as one of the 3 greatest mathematicians of all time. But his combined achievements as the theoretician, an experimentalist, and mathematician put him in a class by himself among empirical scientists.
His honors are global and enduring. The unit of force is named for him.
Right. He was named Time magazine's Person of the Century for the 17th century, and he was voted the greatest Briton in a 2003 poll, ahead of massive figures like Winston Churchill. Even the Nobel Prize-winning physicist Lev Landau ranked all physicists on a logarithmic scale of genius from 0 to 5. The highest ranking 0 was assigned only to Newton.
Wow, just him.
Acknowledging his singular contribution.
Ultimately, the Principia was more than a physics text. It provided the philosophical framework that sparked the Enlightenment itself.
That's the deeper legacy. Newton's publication of the Principia is considered a crucial turning point that started the Enlightenment. His conception of the universe, based on natural, universal, and rationally understandable laws, provided the philosophical seed for Enlightenment ideology across all disciplines.
How exactly did that scientific framework inform political and economic thought?
Well, Enlightenment thinkers took the idea of universal natural laws and they applied them to human society. Think of John Locke and Voltaire, who applied concepts of natural law governing the heavens and earth to political systems, advocating for intrinsic, unalienable rights for humans.
And Adam Smith in economics.
Similarly, yes, Adam Smith applied natural conceptions of human psychology and self-interest to economic systems, seeking the invisible hand that governed markets. Newton provided the clockwork universe, and Enlightenment thinkers sought to find the clockwork governing human behavior and governance.
What an incredible journey through a life that defied simple categorization. We started with the apple, but we ended up with universal laws, a successful war against counterfeiters that stabilized a national currency, and a secret life involving both ancient heretical texts and mercury poisoning.
It's the profound paradox that must stick with you, the listener. The man who fundamentally changed the basis of the scientific method, demanding that explanations be grounded strictly on observable data with his famous rejection of unsupported hypotheses, hypotheses non fingo.
Right.
That same man spent decades searching for the secret fire of nature through alchemy, a field that blurred the line between science and magic.
That seems like an utterly human, necessary contradiction contained within the supreme genius. He had the rational side that wrote the laws of motion, and the intuitive, exploratory side that risked his life searching for secrets in the dark.
It does. And this raises an important question for you, the learner. If the supreme genius of science operated simultaneously on multiple, seemingly contradictory intellectual pathways, the intensely rational and the passionately occult, what does that tell us about the true methy nature of breakthrough discovery?
It's a great question.
What contemporary fields or pursuits, dismissed today as marginal or non-scientific, might actually hold the scientific seed of tomorrow? Something to mull over as you encounter new, strange ideas.
A fantastic thought to end on. Thank you for joining us for this deep dive into the paradoxical world of Sir Isaac Newton. We'll see you next time.